Hello, everybody. Today we'll talk about a case study of how the Doppler effect is experienced by a person in a space shuttle that is re entering the Earth's atmosphere. So, consider a space shuttle entering the Earth's atmosphere. The space shuttle is traveling at an incredibly high speed of 17,500 miles per hour, or approximately 8 kilometers per second, which is very, very high compared to the speed of sound. We assume that the shuttle itself doesn't make any noise because we are trying to investigate how the person inside the space shuttle will perceive the noise outside the space shuttle. We also assume that the sound can travel in the atmosphere at which the space shuttle is located at the same speed as it travels on the ground at about 340 meters per second. And let's consider a stationary source in the atmosphere closer to the space shuttle that's going to generate this 1 kilohertz pure tone. And we intend to determine how this 1 kilohertz pure tone will be perceived by the person inside the space shuttle traveling at a very great speed due to the effect of the Doppler effect. So this case study is predominantly to understand the extreme version of the Doppler effect, like the extreme version because the speed of the space shuttle is much, much higher than the speed of sound. So this is a schematic. The space shuttle is entering the Earth's atmosphere, and there is a sound source that is emitting 1 kilohertz pure tone, and we intend to determine how that 1 kilohertz is perceived by the person inside the space shuttle. Due to Doppler effect, this will be distorted, but it will be distorted to a very great extent due to the fact that the space shuttle is traveling much faster than the speed of sound. So, basics of Doppler effect. The Doppler effect is the apparent change in frequency of sound when there is a relative motion between source of sound and an observer. For example, an observer can be stationary and source can be moving toward or away from it, and vice versa. And also both can be in relative motion with respect to each other. So Austrian physicist Christian Doppler described this in 1842. The perceived frequency can be greater, lesser, or stay the same based on different cases involving the source and observer. So you can check more about Doppler effect in the link in the description below. So this is the Doppler equation. So this equation takes into consideration the speed of sound in air, the original, the apparent frequency, and the velocity of source and observer. So the apparent frequency is some constant times the original frequency, and this constant varies based on the velocity of the source and observer. So we're going to plug in the values in this particular equation. We know that the source is stationary, it's emitting sound, so it's 0 meter per second, it's not moving. Whereas the spacecraft is moving at a very high speed of 7,800 meters per second, and the actual frequency emitted by the source is 1,000 hertz. So we plug all those values in this equation, and we get a frequency of 23,941 hertz. Now, this is beyond human hearing range. It's in the ultrasonic range because we humans can only hear up to 20,000 hertz. So, to conclude, the space shuttle is flying very fast. It's flying almost 20 times the speed of sound, and it's approaching the source. The source is emitting a sound in 1 kilohertz, but due to this extreme Doppler effect, due to the extreme speed of the space shuttle, the sound is shifted in the ultrasonic zone. 23,000 hertz is in the ultrasonic zone. It's beyond the capable of human hearing, which is up to 20,000 hertz. So the astronauts who are inside the space shuttle will never hear this 1,000 hertz because it is beyond their human hearing range. So the purpose was to describe this extreme Doppler effect due to very high speed of the space shuttle. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.